everyone. This is the review video for section 3.2. It's called Doped Semiconductors. As always, you have the key points here on your top left, and we're going to try to cover all those concepts. The first one is doping. So you may ask what is doping, and we have the definition here, which is increasing the carrier concentration by introducing impurity atoms into the silicon crystal. These impurity atoms are important. So let's see how that works. Here on your left, you have an N-type semiconductor. That's the first thing that we're going to cover. But for now, it is just the silicon crystal. You know, you have the silicon, which is four valence electrons that form covalent bonds with other silicon atoms. So each of the atoms has 8 valence electrons, or not 8 valence electrons, 8 electrons on the outer shelf after the covalent bonds. So let's say we get rid of the silicon atom and its corresponding electrons, and instead we add one of those impurity atoms that we talk about. And for the N-type, we're going to add a phosphorus, something for an element from group 5. Right here, group 5. Group 5. Oh, sorry. 5, right there. So an element from group 5 has 5 electrons. So we have 1, 2, 3, 4 electrons. Those 4 covalent bonds with the silicon atoms, but we have an extra electron, and we call this a free electron. It's free to move across the crystal. And with this, we can see that for, let's say we add a lot of phosphorus atoms. So from each phosphorus atom that we add to the crystal, we add an extra electron. So here we can add, what are donors? Donors are elements that donate free electrons. So here we're talking about this phosphorus atom. So every phosphorus atom or group 5 element is going to be called a donor. What else can we talk about? The N-type semiconductor. So N-type semiconductor, we have these two definitions, minority and majority carriers. A minority carrier is what you have left less of in the crystal. So since we're adding extra electrons, what we have less, or what is the minority, is the holes right here. And since we are adding a bunch of electrons, the majority carrier would be these electrons. And lastly, here I have why. Why do we create an N-type semiconductor? That is so that we increase the number of electrons. So you can see I've been saying this a lot. We add a phosphorus atom to create or to increase the number of electrons. Some important definitions here as far as formulas are concerned. If you remember that from an intrinsic semiconductor, the number of electrons right here times the number of holes would equal to the number of intrinsic, the carrier concentration squared. In this case, what we will have is the number, this is going to be the number of electrons, that's how we call it. This subscript right here determines N-type, or means N-type. So this number of electrons will be equal to the number of donor atoms. So this guy right here is the donor concentration. Donor concentration. So for each donor atom that you add an extra electron. And then another thing that we know is that the number of donors, or the donor concentration, is going to be way bigger than the intrinsic concentration, because we want to add more free electrons. So this translates to, if looking to a similar equation like this one that we have right here, if you want to find the number of holes that this thing has, again, the subscript N is for N-type, you're going to have that Pn is equal to Ni squared over the number of donor atoms that you have. And just lastly, since your number of donor atoms is way bigger than the number or the intrinsic concentration, and since you're adding a bunch of atoms, you're going to notice that an N is an order of like 2 or 3 orders of magnitude bigger than the number of holes, depending on how much doping do you have. The last thing that I want to mention about this is, let's look at this phosphor atom right here. This phosphor atom is losing an electron, is donating the electron to the crystal. So since we're losing negative charge, the phosphor atom is going to end up with a positive charge. This positive charge is what we call a bound charge. This bound charge, right here, I'm going to write bound charges do not move. So the other charges, electrons and holes, they move around the crystal. They're free to move around the crystal. But this bound charge is what the phosphorus ends up being, is a bound charge that will not move. It's a positive charge that will not move. And this is going to be important when we talk about p-n junctions a few videos later. Now, let's talk about a p-type. So similarly to the n-type, the p-type is going to be represented, I guess you can guess, instead of having electrons, what we're going to do is add holes. How do we do that? Let's get rid again of this silicon atom and its 4 electrons, and instead of adding atoms from group 5, let's add atoms from group 3. The atoms from group 3, let's say boron is a typical one here, has 3 valence electrons. So here 1, 2, 3 electrons, and we end up with a hole right here. So this hole is going to be free in there so that another electron can come in and fill that hole. These holes, you know, holes are, as I mentioned before, are like a representation of the absence of an electron, and we represent that as a positive charge. So if that positive charge is moving around, this boron is going to end up with a negative bound charge. So just here, similar to the phosphorus becomes a positive bound charge, the boron becomes a negative bound charge. So here on the p-type semiconductors, acceptors are the name that we give to the impurity atoms that we're adding to the doping, to the crystal. So acceptors are doping elements that accept, so they accept, just like the name tells us, accept an electron. And what does that create? Creating holes. And this is important part. So again, we add group 3 elements. What are the minority carriers? So the minority carriers are going to be the electrons, because the majority carriers are holes, which is what we are adding. Holes. So we're adding a bunch of electrons. Again, why do we do this? Why do we dope p-type semiconductors? So that we increase the number of holes. So that we increase the number of holes. One thing that I think I haven't mentioned is n-type are called like that because remember we're representing the electrons with this n, and p-type are called like that because we're representing holes with the substrate p, holes. And similarly to the n-type, here on the p-type, we can create formulas just like this ones. So the number of, come back to the black right here, the number of holes that we have, pp. Now this substrate p means p-type. The other substrate p, the other p right here is holes. So the number of holes is going to be equal to the number of acceptor atoms that we add. So this right here is the acceptor concentration. And similarly, the number of acceptors is going to be way bigger than the intrinsic concentration. And then just because of this, the number of holes is way, not equal, is way bigger than the number of electrons. And if you want to find the number of electrons, what would you do? So you have NP equals to NI squared over PP, or better than NA, because in a problem they will usually give you this NA. So here is everything that you need to know for this section. Remember what doping is. I have the definition right there. What an N-type, what are the difference between N-type and P-type semiconductors? What are donors, acceptors? What are the minority and majority carriers? Try not to confuse them. And what is a bound charge? Okay, thank you. I'll see you in the next video.